very well also. Um, I think Vibu, you went over this plot last time, or was it 2 weeks ago? I can't remember. Where like basically summarize this kind of summarizes what you just said, which is that like they're really just really doing better than the competition for the number of flops that you spend, and like this is another way of saying that with this scaling curve. Um, so then. Why the question, of course, is why does it do so much better? And this technical report is about how they accomplish this and a little bit about why I found that I think there's a lot of implicit knowledge for people who um, like follow optimization that I didn't have. So I kind of dug in a little bit deep on uh, some of the details here. Um, the questions that I had, maybe not the same questions that other people have. So I want to make sure that I'm answering other people's questions. So I'm not keeping an eye on chat, but if you please like interrupt and whatever, um, if you have other questions or I explain something poorly or I get something wrong, I definitely could, because this material is not super familiar to me. So I may have misunderstood something or get a detail wrong or whatever. Okay, so without further ado, so the point of this, so there were some early results with Muon that were really promising, but that the performance of it, the optimization diminished as the models scaled. And so this technical report was okay, but we can do some tweaks and actually scale to large models. And so, but I think a lot of the meat is actually in understanding what's going on here is actually in just understanding Muon itself, which I think was, I don't know that there's actually a paper on it. I think there's a blog post on it. And it's it's sort of an evolution of optimization technique called shampoo, which I have not studied. And then Adam is also, one of the dominant optimizers. And so like, if in case you're like really new, these are all optimizers so you're doing back propagation to train your neural network. And when you do, every time you do a forward pass, then you have some loss, meaning the error between what you predicted, what the neural network predicted, and what it should have predicted. And then that loss is used to calculate a gradient on the parameters of the neural network, so that I know, okay, in order to get closer to where I'm supposed to be, then what's the difference between what the parameter values that I have set currently and what they should have been to do better. And so I do this a whole bunch of times with different data, chunks of my data, different batches of data. And then eventually like that sort of causes what's called the stochastic gradient descent towards the, sort of optimal setting of those parameters. And of course, this is like not a convex problem. So meaning that like when I'm doing gradient descent, when I'm going down the hill, I might get in like a little local valley and get stuck there. But so some of the techniques that we'll talk about are to avoid that. So okay, that's my like really high level introduction to sort of what this algorithm does in terms of the sort of ecosystem of neural network stuff. Okay, so
Um,
so
quick
yeah,
note. So Hamgad has joined, your second co-host. He's joined. Sorry, I had trouble giving him Zoom link.
okay,
So he'll help with presentation. I guess on the background of optimizers. So like
yeah,
you mentioned, there was regular gradient descent, which is you do all parameters, kind of what's the change and update in general. Then the kind of iteration loop for people that haven't really followed is like from there we went to adaptive per parameter. So like AdaGrad, RSM prop, where like, okay, for specific parameters, maybe we change them differently than the whole network. Then Adam had this like the Adam optimizer was pretty big in like 2014. That was like, okay, let's have this concept of momentum, right? If we're moving in the right direction, let's like gradually increase and have adaptive scaling. Adam W was like, okay, we like momentum, but let's separate weight decay because we want weight decay from gradient step to be separate. Then from there is, where we have stuff like this. And this stuff, like, no one has really scaled it, but that's like the little bit of middle ground.
Yeah. Okay. Yeah. Good. Thank you for that. Um, uh, okay. So let's see. So so this, like Viva was just saying, weight decay here, you know, is important, but they had, sort of created a technique to set the weight decay relevant parameter automatically, and so that's one of the things here. Um, they talk about like a distributed version that works. Whoops, sorry. Let me undo that. Um, that works with zero, meaning the zero is, what does zero stand for again? Vibu, help me. It's so zero is like, sort of like fully parallelized across multiple dimension training. So
Multi GPU and stuff. They
yeah,
have zero,
multi,
zero, 1, 2, 3
yeah,
different levels of distributed
yeah,
training.
right.
So
Um,
it's a efficiency, right? So instead of like having all weights on all GPUs, there's different degrees at which you can do zero optimization.
yeah.
And this is compatible with zero.
Yeah, so they're previously had some problems distributing, and so that this is how do we do that? So this is basically essential for actually scaling to a large model. Um, and then they look at the scaling laws and compare to Atom baseline, and it's it's sort of like way better. So right there. Okay, so the thing that I actually got out of the paper was more just Muon and not these 3 points here, which I think are to me are kind of like more engineering-y, and so like definitely other people will have different interests here, but I thought the thing I can do is really understand uh, what's going on here and as best I can and try to explain it to you guys. So like this is the sort of like core algorithm, right? So you have this momentum, this M here, and the momentum is just at every time it starts at zero, all zero, and then so like if this is M, if we're at MT minus, if we're at step one, I have, I'm forming my first one, then it's just going to be the loss, the gradient of the loss function on the weights. Okay. Every time I'm taking like a trade-off between so this mu parameter kind of trades off between the momentum and the loss. And so this determines how much do I pay attention to the past versus the current gradient. Okay. And then this O step is kind of the core of what this algorithm is doing. And this is what they call orthogonalizing the the matrix. And so I actually didn't understand what they meant by that because like if you think about, if I don't, and again, I will I'll try to like play a middle ground between people who understand linear algebra well and those who don't. I'm somewhere in the middle. I don't have great linear algebra, but I have a reasonable understanding. So like if you look at singular value decomposition, which is how you would calculate an exact eigen decomposition or singular value decomposition of a matrix, you would that's like a expensive, very expensive thing to do. And so this Newton-Schultz algorithm is just a way to is sort of like a way to approximate that, but it's not quite because when you do a singular value decomposition, you're getting like these specific set of outputs that is like the eigen values, which is like the sort of amount that I'm moving in, that my transformation scales things in different directions. And then like the eigenvectors, which point in which directions. And so I was a little confused about what they mean by an orthogonalizing a matrix. So the way, so I kind of like had to do the, you know, sort of little diagram here. So sorry if it's a little bit scratchy, but you can think about, so let's just look at this n by d matrix here. And you have, so I just picked arbitrary values. And so d, like in our case, just to keep things concrete to what we're talking about here, d is like the pretty much the hidden dimension of the neural net or of a given matrix. So this is done per weight matrix, not for the whole weight matrix. So like it's basically the hidden dimension. Like it could be, so depending on which one, it could be like some multiple of the hidden dimension or whatever, but it's kind of generally that order of magnitude. And so we're talking like 4096 or something like that. And then the n here is the batch size times the sequence length. So batch size is, I don't know what, like somewhere between like 256 probably to, I don't know, a couple thousand. And then the sequence length is what we all talk about, the context window length, right? So that could be, yeah, I think they mentioned in the paper for the trainings that they did, they were at 4,000 and 8,000. So these are like in the millions, basically. So like much higher dimension. So my N is more than my D, right? And so that what the key observation, one of the observations here is that this is low, that like a reduced rank matrix, meaning I'm on a subspace of the total number of dimensions. So for example, and if n in this case is 3 dimensions, so I have these 3 blue lines that kind of sort of try to draw this 3-dimensional space. And then I have these 2 black lines, which try to draw, there's a plane that are defined by these 2 vectors, right? These 2 3-dimensional vectors. Those 2 define a plane. And then what I'm doing by orthogonalizing is I'm just finding 2 unit length vectors that are on that plane that are orthogonal to each other. They're perpendicular to each other. And so that and it like you'll notice there are infinite number of these, so it's not a unique solution, but that I'm just, and okay, so we'll talk about why, but that's what's going on here, is that that's what this Newton-Schultz thing does. So, and this is actually not in the weights, this is in the gradients of the weights, right? So what's going on here, and they talk about the intuition, and I'll give it a little bit right now, is that there's this momentum term, and the momentum is like, I'm sort of keeping track of where I was going before and making sure that I can continue in that direction, sort of. And I'm doing that so that like if I have a little valley, if you can imagine yourself being a ball rolling down a hill and you get into a little valley, then maybe you don't have enough, then you end up like, you know, stuck in that valley. But if your ball is heavy enough, then maybe it'll roll up the other side and keep going down, right? So that's sort of the intuition why they call it momentum. And so what this is doing is saying, rather than like a lot of my momentum going in this one direction and only a little in this direction, I'm saying my momentum, I'm stretching that matrix and changing that so that it can kind of go in, the momentum can kind of go in equally in all these different directions that are defined by the data. Okay, that's very vague, I know, but like that's the intuition. Maybe I should stop here because that's like, I just said a lot. What do you guys, are there any questions in the chat or anyone want to like sort of ask about this? Okay, if not, I will continue. So I'm actually going to skip back and forth here because I think that the sort of, I will talk about that a little more. So they actually have an interesting section here. Where is it? Where they validate this concept. So, so this dynamics of singular spectrum. Okay, so what they did was they looked at, so there's a concept of entropy. Again, if you're not familiar with the math, that's fine. What the entropy measures is the sort of like the amount of like variation. It's not quite variant. It's not variance, but it's the amount of, I mean, technically it's the amount of information in a distribution. But if you can imagine like a probability distribution, you could have like a really, really sharp distribution and it always picks one value. And that would be very little information, right? Because I always pick that value. So I know I can't express anything really with that. I can't even express a single bit of information. If I pick one of two values, then I can express, some more. And if I have a uniform distribution, then I can express lots of different values. So that's like higher entropy. So it's like a measure of the amount of information you can express and the sort of randomness of a data set. And so what they did was they sort of abused um, based on another paper, which I didn't read. But so you get this like entropy equation. And if you've seen entropy before, you'll recognize that this is basically just, this is my distribution. So I'm sort of taking my eigenvalues, I'm squaring them and taking the sum of them so that it becomes a probability, and then I take the log and so it becomes an entropy, right? And so multiply by the log and it becomes an entropy. And so what they're doing here is they're saying, like sort of, if I have a lot of, if my weight matrices have a lot of sort of like are pretty spread out and flat, then if I'm tending to cause my weight matrices to be like sort of quote unquote orthogonal, so that I like have lots of different directions in them, then in sort of like my rank is high, then or sort of like the dimensionality of the embedding space maybe is a better way to put that, then like I get a high entropy here. And so what they found was that compared to Atom, they do a lot. They have like, where is it? This right here. So that basically this is like empirical evidence. So they had higher entropy in the weight matrices than the equivalent models trained by Atom. And so what they're saying is that we were able to explore dimensions more effectively, is sort of what, and so this is kind of the why. And this is like really fascinating to me, is that like, and so that they talk about this a little bit more. Let me find it, right? Right. Yeah. So, sorry. They talk about this, sort of like viewing Muon versus Atom as using different norm constraints, meaning they're sort of basically regularizing in a different way. And so they're saying, whereas Atom is sort of, and so like, and I think I have this right. So, somebody knows better, please correct me. But what Atom kind of sort of is doing is saying, I'm looking at these vectors kind of, or these dimensions, and I'm taking the maximum size of that, and I'm constraining my momentum by that. Whereas the Muon optimizer is instead looking at the largest eigenvalue and constraining by that. Okay, so that's sort of the fundamental difference, and that makes sense because it's not because things are happening in this eigenspace, not in in these like sort of dimensions, right? Because you can rotate things around in the embedding space. And so that it doesn't make sense to constrain your optimization direction because you might have one direction that is really large because of all these different directions that are summing up. Okay, so that's a really mumbo jumbo explanation. I can go into more. Um, I can go into more, but I think I've probably talked about this much. Does anyone want to ask a question or should I move on? Okay. Okay, so I want to make sure that the other speakers have some time. So I'm gonna like sort of like brush over all this stuff and then we can go into any detail either at the end or as you can interrupt me and uh, I'm happy to go into details about these things. So but like okay, so what are the key things from this paper now that I've like made a half effective maybe attempt to explain like the core concept here. So
Quick,
so I think that yeah, go ahead.
quick question. So Yikes has said in the chat, if you can repeat what Atom looks like versus this, looking at the eigenvalue, like in the math, your interpretation of the math, us comparing these.
Oh, okay. So let's see. Yikes, you wanted like this kind of explanation again? Is that right? Okay. Yeah, okay.
Constraints.
Yeah, so basically like um so my and again that you know some hopefully somebody who's more knowledgeable can correct me if I'm misunderstanding, but what it basically like each one of these vectors has a size, right? And if you look, and I'm not going to go into the math of why, but um, effectively that the norm, the sort of constraint that Adam is using in effect is that the biggest one of these vectors, you're normalizing by the length of that vector, right? So you have a whole bunch of, this D is in reality like, big. And so you have all these vectors and you're kind of normalizing by the biggest one of those. And the problem with that is that you might have a direction in like you could rotate so that you're squishing in some direction that is a sort of combination of these different vectors, and that would be like the largest eigenvalue, right? So and so that what effectively you're doing with Muon is you're in the spectral in spectrum space, which is like the eigen decomposition space. You're constraining the size of the jumps, the steps, or the sort of strength of the momentum by the largest direction in eigenspace instead, right? So you sort of like look at what are the principal components of this um, of this or the eigenvectors and looking at the size of those and looking at what is the largest eigenvalue and dividing by that, basically kind of sort of normalizing via that. Does that make any sense? Okay. I'm happy to like discuss this, and I think I have a reasonable grasp on it, but I may not. And so like happy to be corrected and happy to discuss this. And it's super fascinating to me and happy to discuss it in great detail. Let me just touch on all these other points and then we can talk about Kimi. I think that I don't want to take up all the time. So like this weight decay, actually, I think the way I kind of read it was, so if you look at the difference between this weight update here and this one here, they're just adding this lambda w t minus one. And so that what they're saying is that I'm I have a controllable parameter that allows me to subtract off some fraction of the weights every step so that like I tend to favor smaller weights, basically. The same reason we do weight decay in all other algorithms, and it doesn't look any different there. And so that they have this algorithm, and then this is basically should be familiar if you've ever looked at weight decay before. And then what they're saying here is that the RMS norm that they use is actually doesn't that you use in Atom doesn't work well for Muon, and I think this was one of their primary contributions here, was that in this paper, is that it's actually it depends on the shape of the matrix that you're normalizing around. So so that this AB, it's the max. So the RMS is the max of these two things, or you can maybe I highlighted the wrong place. So that like when it's large, then you're dividing by a, like the large dimension, and when it's small, then you're not normalizing enough. And so that you either get, sort of like gradient, you get explosions or your vanishing gradients if you're not careful. And I think that they hypothesized that this is one of the primary reasons why larger models were running into trouble. So because of that, they had a few different mechanisms for updating, and they did some ablations down here, but I think they came up with just multiplying out like this, right? So that so now this equation here has changed to this. So they're just adding, and they have this 0.2 to match what Atom does, and then they and that's like a minor detail that you probably don't care about, but they so they do this normalization so that they can they are now independent of the size of the matrix that they're doing the update on. And so this is one of the key things that allows them to be stable with larger training runs. Okay, and then what are the other things? So then they also, like, and we kind of touched on this, the zero and sort of Megatron LM, which is like even more complicated parallel strategies. So they basically have an algorithm here that they describe. I don't think that there's a whole lot here, but like you can go through it. It's just like they just gather some more. They've kind of changed how you do the updates to gather information. The one thing that I found was interesting was this line. So they actually discard. So I think what they're saying is that on each node they're actually calculating they have to do like the entire. They have to calculate the entire momentum matrix and then only apply it to the parameters that they care about. So this is a little bit inefficient, but they talk about how despite that inefficiency, they because they're only using one momentum buffer instead of two, that like, okay, from a space standpoint, that doesn't matter too much. The communication overhead is like slightly higher, but because like as you scale, it matters less and less. And then sort of like they found that in practice, the sort of the end-to-end latency increase was pretty negligible. So like, and then finally, this was like evaluation of some different strategies for doing consistent update in the weights, or sorry, in the momentum term. They, like I said, they landed on this one. You can read more detail if that's interesting. And then they, they had some interesting scaling laws here. You can see that, like sort of Atom does not surprise, or sorry, Muon not surprisingly does better, and they fit. I didn't find their curve very convincing that this is actually the right fit, but you know, I didn't, whatever. It's clearly much better than Atom, so I'm willing to take it. And then let's see what else. I'm sorry this is so rushed. I really didn't have a time to prepare super well. Um, but oh yeah, this section I thought was really interesting as well. So this I talked about the entropy measure that is right here. I talked about that previously. I think that this is a really interesting set of plots where um, the um, the weight matrices um, have, you know, throughout the, you know, so if you look at Atom as red, so this is Atom, and then Muon is the blue one, and these are different parts of these here are different parts of the model and different training iterations that like the entropy in the weight matrices is, you know, tends to be much higher, meaning that the weight matrices are expressing different things more effectively than when you're trained by Atom. Different, so they're using the dimensionality of the weight matrices more effectively. Is I think the summary of that. Um, and one, so I'll conclude now, I think, but one like interesting thing that so they found, so I found these two sections together quite interesting. Whoops, these two sections together quite interesting. So if you pre-train using Muon, then like like everything's better, basically, kind of sort of. However, and they talk about like different like for um, you know, sort of like pre-training plus fine tuning. Oh, sorry. If you pre-train and fine tune using one, they do better. Um, however, they found that if we take public models and they're obviously already pre-trained on whatever optimizer, and then they do the fine tuning using Atom versus Muon, Atom does better, right? Consistently. And so that is one of um, the primary questions that they had. It was why does that happen? So, and I don't think they don't really think they had a good explanation for that at all. Um, okay, so yeah, so I think that's probably enough. I want to make sure that other people have time to spend, but maybe we should, if there are any more questions, I'd be happy to answer those, and then I'll hand over the reins. Any questions? I know this was like really rushed and maybe not super intuitive. Um, I apologize for that.
Not at all. Like this is as good as we can hope for explaining like this kind of optimizer work. I think Amgad had some commentary. Eugene has actually used Muon. Um, either of them. It looks like Amgad is coming.
Yes, can you hear me? Am I
Yeah,
audible? Okay, cool. Yeah, I did some remarks about how they even scaled Muon further in their training of Kimi K-2. I can share like the notes and can quickly go over them if there are
Okay,
no
so
other
yeah, this
questions.
is the clip stuff. Yeah. Yeah, I think RJ, you're gonna have to stop sh the share so that Amgad can do it or whatever, however this works.
yeah, okay. Give me 1 second. Let me figure that out. Here we
I mean,
go.
yeah, Zaxis is Mathian dense, so any attempt to describe it is inherently Mathian complex. I actually like thinking about like use this in terms of theory of learning. So I think there's a lot of ways in which you can apply the algorithms to your own personal learning as well. So like the concept of momentum to me is something that I tell people about a lot. When you are wrong, you should not only update to what you were wrong on, but also have momentum on further updating. Um, I'm glad. Are you sharing your screen?
I'm about to. Should
Yeah.
be
Can you
And then,
explain
should be
your
visible
design?
now.
yeah, cool. Yep, yep. All visible. I'm good. I don't know if you're speaking. He is not speaking. He has killed his voice. Okay, someone else explain his blog.
Is it
Okay. Yeah.
okay? Is the screen visible now?
Yeah. You're good. You're good. Yeah, you can go.
Okay, cool. Okay, cool. So hi everyone, my name is Amgad. I'll be sharing some of the notes I took when researching the K2 model. Most of this comes from the blog post they published. They said they will be sharing a very detailed technical report, but we can never know. So I'll just go ahead and share whatever I know right now. So let's start with the architecture. Basically, how they designed the model. They had a few principles they needed to follow, and they did a lot of scaling experiments before the training even started. So they run a lot of scaling experiments at a lot of the details that you can do, or a lot of the changes you can do to the architecture. And they found out that every single detail, every single change they made didn't improve the model at all. And sometimes it was just worse. So basically, they decided to stick with a DeepSeek v3 architecture instead of just changing for the sake of change. And I think this is a very good approach that we don't see a lot. Like people want to try different stuff because they're just different without having any justification for using them. So yeah, their answer was no, we should just use DeepSeek v3, and then maybe you can make some even further scaling on top of it, rather than making new changes to the architecture, because they already have a significant change, which is the optimizer. They are now using Muon instead of AdamW, which is the industry standard. So they had a few constraints when trying to scale this up. The first constraint is it should be as close as possible to DeepSeek v3. The second constraint is the cost ceiling. They are a small company and they don't have a lot of money, so they want to keep training and inference cost as low as possible. So they did a lot of experiments, and they found that DeepSeek v3 is at the upper limit of what they can afford. So K2 must be similar to DeepSeek v3 in terms of cost. So with these two constraints, they actually arrived at a conclusion that they should use the DeepSeek v3 skeleton and then find parameters that keep the training and inference cost at the same, but while like reducing the loss significantly. So they made a few changes. We can go over them now. The first change comes from something called the sparsity scaling law. This is an internal experiment, or like an internal series of experiments that was done by their pre-training team. They found out that with fixed activated parameters, if you increase the total parameters of a mixture of expert, it still obeys the scaling law. There is no overfitting and the loss keeps going down. And this is internal research that has not been published yet, so we just will take their word for it now. So based on these observations, they decided to take an action to increase the total number of experts to 384 compared to what DeepSeek v3 is using, which is 256. The main issue with increasing the total model size is assuming that you have a fixed number of nodes, a fixed number of GPUs. Now each GPU is consuming more and more memory because you are having more total experts. So in the new K2, you have 3 experts per node, plus the one shared expert, which consumes about 10 gigabyte, compared to DeepSeek v3, which used 2 routed experts and 1 shared one, and used 7.5 gigabytes. So right now, the model is consuming more memory. I think it's almost, they say it's 50% more. I didn't double check the math, so we can just take this for granted. But they are saying that now we have more memory consumed. We want to claw back this memory because memory is valuable and compute and bandwidth are like limited resources for them. So they made the second change, which is reducing the number of attention heads. The DeepSeek V3 initially doubled the number of attention heads, and they justified this because they said this maximizes the bandwidth utilization. So this is something that is a bit more specific to the DeepSeek V3 infrastructure. So the Kimi K-2 authors decided to reduce the number of attention heads to 64. And this results in two main points. The first one, we're cutting the head in half. So this means we're getting like huge wins for long context. And this is important for K2 because it's going to be used for agents and vibe coding and consuming tens of thousands of tokens to do vibe coding stuff. So this is quite important already. The second result is that the query and the key and the value and the output projection, these parameters are reduced in half because we're using half the heads. So this goes down from 10 billion parameters to 5 billion. So we are cutting the flops used in a significant portion again. And they have done a lot of ablations internally that show that the negative impact on the loss by reducing the number of heads is quite minimal. And again, we will have to take them for granted on this. The third change they made in the architecture is they are no longer using expert grouping. So grouping helps when you have more than one expert on a GPU, because this tends to balance the work at the device level. They said that they have a certain requirement for scaling and that they are actually using one expert or even less than one expert on each GPU because they need to serve many numbers of concurrent requests. So at the current scale, if you are having one expert per GPU, you don't need to group the experts because you're just routing to each node. So they said that we no longer need any expert grouping. We can just use the router and give it more freedom. And this allows them to explore more of the combinatorial space and arguably have better model quality. So these are like the main changes in architecture compared to DeepSeek V3. The summary is it is a sparse mixture of expert model. It has 1 trillion total parameters, sorry, not tokens, but only 32 of which are activated in each forward pass. It is quite similar to the DeepSeek V3 and R1 architecture because it's basically an evolution of it. It's using less attention heads, but has more total experts, and it has a bigger vocabulary size. It's now using 160,000 tokens instead of 129,000 tokens in the vocabulary. And this is a nice graph comparing the two architectures by Sebastian Raschke. So please go and check this. I'll be sharing the notes in the Discord server after the meeting. So this is regarding the architecture. Any questions before we cover some of the training approaches and other contributions? Can you guys even hear me? Can just someone confirm that we're all good?
We can,
Yeah, we can hear you. We can hear you.
I do see one question in chat. I'm not able to digest how to find the best momentum and weight decay of the Muon optimizer among different attention heads among all the MOE.
Maybe I can, if I understand that question correctly, the momentum term is per the momentum matrix is there's a different momentum term per parameter, kind of sort of. So like each attention head and each expert matrix will have its own momentum direction. Does that make sense? So they're all calculated separately is kind of another way to put it. Does that answer the question? I'm not sure if it does or not. That was from Osama, I guess. Okay, good. Awesome.
Yeah, sorry, I disconnected for a while.
No worries.
Before disconnecting,
I-
I was
Yeah, I answered the question anyway. Perfect.
okay. I was asking if there are any questions regarding the architecture, but I think we have no further questions, right?
I actually do. I heard that it was 1 trillion tokens and not 1 trillion parameters. Okay. Oh, is it so it's 1 trillion? Is it yeah, what how many tokens and how many parameters?
Yeah, so the total number of parameters, though the size, let me just correct this quickly. The total number of parameters is 1 trillion, but only 32 are active. And this is compared to DeepSeek V3, which has, I think, 670-ish total parameters, but only 36-ish are active. So
Okay.
yeah, this is regarding the total size. So if you were to download this model on disk and assuming 2 bytes per token, you're gonna need like 2 terabytes, I think, of memory to just download it.
Yeah, I was mostly wondering about the distinction between parameters and tokens, but it sounds like 15 trillion total tokens that it was trained on, and then 1 trillion parameters is what I'm hearing. And
Exactly,
then
yes,
32
yes.
active. Yeah. All right. Cool. Sweet.
Yes. Yeah. So yeah, this was regarding the architecture. We can now go into details about some of the motivations and the principles behind their approach to train this model. So they have 2 big principles. The first one is the agentic intelligence. They believe that LLMs should be agentic and they should be intelligent. They should be able to use tools in an intelligent way, tools to write down summaries and like insert new information into memory and access MCP tools and all of this amazing agentic capabilities. And they also think that the model should be intelligent to know which tool to use and how to use the tool. Basically, this principle comes from reinforcement learning, and that to do a really good job at reinforcement learning, you need 3 components. You know, the algorithm, and the environment, and the priors. The main point is without good priors, the agent is just going to randomly guess what action to take when interacting with the environment. And this was going to result in a low reward because you're just randomly guessing which tool should I use or which action should I take. And you're not gaining a lot of rewards and you're not improving. This is going to make the training, the training process of RL is going to be very, very hard. It's going to take a lot of time because you're getting a very little or like very weak feedback signal. But in the last 2 years, the pre-training of large language models has made them almost universal models. They have great world knowledge. They know a lot of stuff, about a lot of domains. So the pre-training of modern LLMs is the crucial foundation for establishing the priors that are needed to develop strong RL models. We have one caveat though, is that the human data is a finite fossil fuel. This is a saying by Ilya, and that the data is like not catching up to the progress of compute. We're getting more and more powerful GPUs every year, but the data is limited, at least the natural human data. So this means we need to be token efficient, and token efficiency means given a fixed size data set, how can we learn more? How can we develop more agentic model and like smarter models and more intelligent models given a fixed amount of data? And we're going to give it like a quick hint that we should maybe look into better optimizers. So optimizers that can achieve a lower loss given a fixed size data set. And obviously the ended up using Muon clip that RJ explained in a good way. The second motivation or principle is the post-training. So we're basically in the what people call the era of experience. LLMs are increasingly learning from their own self-generated interactions. They're not just relying on the data that we create, the instructions that we write for them on how to solve the problem. They're actually learning from their attempted solutions at the problem. And there are like 2 examples of this. The first one is alpha proof. So this model was initially trained on like around 100,000 proofs written by human experts, but then it went on to generate around 100 million more by interaction with the environment and receiving rewards using a formal proving system. This allowed the model to basically improve significantly and become way more capable compared to previous models. The second one is the tried and tested DeepSeek R1. It uses verifiable problems like coding and math. Basically, we give the model the problem and it makes a lot of attempts to solve the problem. And we just judge or grade their solution. We can say, okay, you're getting close, you're getting not close, you're doing good, you're doing bad. And this allows the model to learn from its own solution without having to write detailed instructions of how to solve the problem actually. So given these two principles, they made a few contributions to achieve these goals. The first one is the Muon clip optimizer. Basically, how can we become more token efficient during training? So as RJ explained, AdamW has been the dominant optimization algorithm since 2014, 2015. And since then, people have been trying nonstop to improve upon it. But I think it was only recently that that like a more prominent approach was discovered by Color Jordan. Basically, the Muon approach to train Nano GPT to a SOTA level. So just want to give a quick overview of how Muon went into Muon Clip. So basically, before even K-2, the MoonShot team was working on something called Moonlight, which was an attempt to scale Muon into an actual LLM, a modern LLM, because Nano GPT was, I think, 100 million parameters. So they wanted to scale this to something that is 3 billion parameters or even more. And they successfully demonstrated that you can actually scale the Muon optimizer into a modern LLM, and they train what they call Moonlight, which is the model trained by the Muon optimizer. Now they wanted to scale this algorithm even further into something the size of DeepSeek V3 or even more. Now we want to train a 1 trillion parameter model. This is quite huge. So when they were trying to train this new model with the algorithm, they ran into a few issues and they came up with clever solutions for it. So they decided to reduce the number of heads for long context efficiency, and they increased the sparsity, but they encountered that a lot of training instability due to mainly exploding attention logits. And this occurred more frequently with Muon than the AdamW. So this is a big problem. They tried it. They tried some of the existing solutions like soft capping the logits and normalizing the query key parameters, but they didn't help a lot. So they offered a clever way to rescale the query and key parameters. They call it the QK clip technique. Basically, it tries to stabilize the training by rescaling the weight matrices of the query and the key projection after the updates. We can take a look at the math here. So after we have the inputs and multiply them by the weight matrix, we scale it by a certain factor for the query, and we also scale it by a similar factor for the key. If you multiply these both together, you're going to get the query multiplied by the key, and both of them are now scaled by a factor. And this scaling factor, it's called an adaptive factor. I think this symbol is eta. Basically, it has a way to calculate it by using the maximum attention logit in the previous step. I'm not going to go into details about the math. You can take a look at the equations and try to understand the intuition. But basically, they're trying to have a soft capping on the values of the query multiplied by the key. And they obviously did a lot of training and training experiments, and they showed that one clip can effectively prevent the explosions while maintaining the downstream task performance. And this is, I think, the highlight of the Kimi K-2 model. They show us the loss curve while training the model. So this very big model was trained on 15 trillion tokens. So this is a massive training run, and they used Muon clip, and they say that they didn't encounter any training spike. And this demonstrates that Muon clip can be stable and robust for training state-of-the-art large language models. And even more, you can notice a second dip in loss at around 11 trillion tokens. And this is quite awesome. So yeah, the first contribution by the team is scaling Muon by developing Muon clip and training the model on 15 trillion tokens in a stable and robust way.
Real quick, I had a question with regards to the soft cap logits technique that they addressed. Is that what's the relationship to that with softmax, or are they essentially the same thing? Are they describing the same operation?
I don't think it's related to softmax. I think they're just trying to put a limit on the value of the query and key, because they noticed that during training the value of multiplying query and key kept going up and up and up, and this exceeded the range that can be represented by BF16 values. I don't think it's related to softmax. It's just like a way for them to control the values without explosion, I think.
Okay, cool. Yeah, good. Thank you.
Okay. So yeah, this was their first contribution, the Muon clip, which allowed them to do a very successful pre-training run. The other contributions are related to the RL side of things. And they did two contributions. The first one is they generated a large-scale agentic synthetic data set. So basically, how do we teach the model sophisticated tool use capabilities? And their approach was to develop a very comprehensive pipeline that generates synthetic data to train the model. So they start by evolving hundreds of domains with thousands of tools. And evolving here comes, I think, from the evolve instruct algorithm by the Wizard LMT. So you're trying to create more and more domains and trying to make them more complex, starting with I think, fixed seed of domains. And then once you have these domains, you can generate hundreds of agents with diverse tool sets. And then you can create a simulated environment and user agents to interact with these agents. And I think user agents means just an agent that acts as a user. So submitting queries and questions. And then they use tasks that are rubric based, basically tasks that are easy to gauge or easy to judge. And they use this to basically judge and evaluate the generated dataset. And then they start the simulations. They run multi-turn tool scenarios with their agents, interacting with the environment and the user agents. And then they use LLM as a judge to evaluate the results, and then use this judgment by the LLM to filter for high quality training data. This is a nice diagram from their blog post as well. So basically, you start with a list of domains that have been evolved. You evolve the domains to generate tools, and then maybe use some MCP tools, and then give these tools to agents, which interact with user agents and the environment. And then you have these tasks that you can evaluate easily, and then use the LLM as a judge to filter and continue the generation and evolve more and more. So this is quite an highly iterative loop that allows you to generate high quality data. So basically, eval-driven training, I think, or I should say eval-driven synthetic data generation. So this is the first approach regarding reinforcement learning. The second one is general reinforcement learning. So we already have RL for verifiable tasks, thanks to DeepSeek R1. They basically train the model on code and math, where the model generates a solution, and then they run unit tests or evaluate the math solution and use this as a signal to the model. Now, the key challenge is how can we expand RL into other types of tasks, especially the ones that are not easily verifiable. Examples of verifiable tasks are like math and competition coding, while writing a research report or a summarization is viewed as a non-verifiable. So they created a general RL system using a self-judge mechanism. Basically, they used the model to act as its own critic, providing scalable rubric-based feedback for non-verifiable tasks. And one cool detail here is that they used the on policy rollout with verifiable rewards to continuously update the critic. So basically, you have some tasks that are verifiable. You can track the performance of the model on these verifiable rewards and see if you're actually, if the model is still going better and better. And this makes sure that the critic model keeps improving its evaluation accuracy. So this can be viewed as a way of using verifiable rewards to improve the estimation of non-verifiable rewards. And these are like the three main contributions by the team. The first one is the Muon clip optimizer to allow them to train up to 15 trillion tokens and achieve lower loss while having the training being stable and robust. And the second one is synthetic data generation for tool use. And the third one is to generalize the RL into non-verifiable rewards. So I think that's all I have to share. This is all the information extracted from the blog post. Just one fun fact here regarding the Muon optimizer. This is Keller Jordan, the main author behind the optimizer, and he said when he was interviewing with OpenAI and XAI, the XAI team told him that they don't think the idea of developing Muon is going to work. So I think, yeah, sometimes you get rejected until you can prove that the algorithm scales. And these are like some references. I used the blog post and the tweet of Sebastian Raschke and the translation of one of the engineers about the reasoning for modifying the architecture of the model. So yeah, that's all I have to share with you guys. If anyone has any questions, please go ahead.
Yeah, I asked it in chat, but they mentioned that they have the sort of self-judging RL framework. Did they like release the code for that anywhere, or was it just like something you found in a blog?
I don't think they shared anything besides the weights and the inference code, unfortunately. So yeah, this is just inferred from the blog.
Sure.
I think that's it for time. Amazing. We actually covered Kimi. I just put it in there because I was like, maybe there's not enough on just Muon. Fun fact, Kimi is now powering all the LLM responses inside of the Discord. So whenever you see a summary from Yikes's bot, it's Kimi because Gemini is the
Yeah.
She's on free tier on Open Router, so I figured we'd give her a shot.
Yeah,
I
I think we have a thread on the Discord server about which providers are serving Kimi K-2.
Yeah. I mean, it's given that it's free tier, so we're not using any tokens, we might as well just like enable that bot to chat more. Because right now it only summarizes links, but it's pretty useful.
Yeah, you can add her. Like she'll talk. I'll double check to see if she's got I don't know if she's got. I think I should be able to. I'll double check her chat model, but yeah, you can add her and she'll chat.
Cool. All right. Okay, lots of people need to go. I need to go. Thank you everyone. Thanks, Amgad. Yeah, people want your write-up.
Yeah,
So
I'll share it in the Discord server in like a few minutes.
okay, bye everyone. Thank you so much. Thanks, RJ.
Okay, goodbye.